take a look at today's lesson. Today's lesson is on continuity. The definition of continuity is a pretty big deal. You will see this in different kinds of contexts on the AP exam, so that's pretty important that we really understand what it means. A function is said to be continuous at x equals c, so at one location, provided that these following three conditions exist. Now, as I go through, I'm going to explain how I might ask this on a formula quiz. For example, this would be like 3 questions on a formula quiz. I might say, what are the 3 criteria for continuity at a point, or definition of continuity at a point? And you would need to be able to tell me these 3 things. Okay, so that's an example of a future formula quiz question. So the first item is that f of c, the function value, must be defined. There must be a function value at c. The second criteria is that the limit at c must exist. And the third criteria is that the limit at c must exist the function value at c. Okay, so let's talk about how that works. I'm going to draw basically just a function. We're going to call this c. Okay? So f of c, is there a function value at c? We would look at c and notice, yes, there's a point at c. The function value is defined. Next is, does the limit exist at x equals c? And we look at the graph and we see both from the left and the right that we're approaching the same value. We could just call that value 2. So number 1, we would say f of c is 2, so that exists. Number 2, we would say the limit as x approaches c of f of x equals 2. Okay, that's also 2. And the last criteria is that the limit value must equal the function value. So my third step is the limit as x approaches c of f of x equals f of c. That's what I need, are those 3 criteria to prove that a function is continuous at a point. Okay, so we may ask ourselves, well, when might that not be true? How is that going to work? Well, what if I had a situation where it looks like this, and this is c? Okay, so let's go through the steps. Number 1, does f of c exist? Yes, f of c is 3. So the answer to number 1 is yes. Number 2, does the limit at c exist? It does not. So the limit as x approaches c of f of x does not exist. Therefore, that pretty much throws out the possibility for our third item. So the limit as x approaches c of f of x does not equal f of c. Okay, so that's a scenario where it's not continuous at that point. So that just kind of demonstrates two examples. Here is where it would look if it was continuous at the point, and this is one example of where it would not be continuous at the point. Okay? It is possible for the limit to exist and this still not to work. I'm not going to go through all the steps, but I want you to consider something like this. Is the limit going to exist here? Yes. And the function value will also exist, but the limit value and the function value are not going to be the same, so it's not continuous at c. Okay, are we okay with that? Okay, it's pretty important. All right. So continuity on an interval is also important. It's not quite as used much as the continuity at a point, but we still need to understand what that is. So to determine whether we're continuous on an interval, we have 3 criteria that we have to abide by. So number 1, the function must be continuous on the open interval. Okay, so we must have some way of determining whether the function is continuous on the open interval. Number 2, the function has to be right continuous. Okay, so that's some fancy words. Let me explain what right continuity means. This is the mathematical notation for right continuity. What it means is the limit, so let's talk about this. The limit as x approaches a from the right of f of x equals the function value. So let me draw a picture here where we have a and b. Okay, so we are on a closed interval. We're on a closed interval, so a and b. We're going from a to b. So the limit as x approaches a from the right of f of x must equal the function value at a. So as I'm headed to the right, does the limit from the right equal the function value at a? It does. The function value is that point, and the limit would approach that point. So this would say this is right continuous. All right, so let's talk about left continuity, continuous from the left. That's our third criteria to prove that it's continuous on an interval. So this is what mathematically looks like. The limit as x approaches b from the left of f of x must equal f of b. All right, so as I'm headed from the left and I'm headed towards this location, the limit is approaching this location, and the function value f of b is that exact location. So we are also left continuous. Okay, a little bit stranger concept perhaps, but we do need to understand what that means, left continuity and right continuity. We're really just looking at, you know, half of it. It's like this is continuous from the right here at a. Is this left continuous at a? No, there's nothing over there, right? So this is to prove that we're continuous on an interval. Okay? All right, the last thing on this slide is talking about the different types of discontinuity. We have a removable discontinuity, which is a hole. It's really the only removable one that we have. We have a jump discontinuity, and we have an infinite discontinuity. And let me show you examples of each one. I'll draw them up here for you. Get some room over here. So I've always thought it's kind of strange that that we have a removable discontinuity. We can remove it. So let's talk about what that is. So here would be an example of a removable discontinuity. There's a hole right there. Okay, let's say there's a hole at, we'll just call that A, and that's 2. So the reason they call it removable is a mathematician can actually rewrite this as a piecewise function and plug the hole. Okay, you can do that. I think that's kind of cool. It's like mathematicians just make it work how they want to. We're going to plug that hole. So we would write it as a piecewise function. Let's call this f of x. So f of x would equal the function here, and again, whatever function this is, when x is not a, and it would equal 2 when x is a, and that would basically just plug that hole in. Okay, that's how you would remove a discontinuity. And really a hole is the only thing you can remove, one point. You can't really remove like a huge chasm, like a jump. You can't remove that. You can just remove a point. So that is a removable discontinuity, the hole. A jump discontinuity, an example of that would be something like this, where you're traveling along, having a great time, and then all of a sudden you just come to a screeching halt and you have to jump to get to the other piece, and then you can just continue traveling along. So that's a jump discontinuity. And the last one, an infinite discontinuity, that's where we have our lovely vertical asymptote. That would provide us an infinite discontinuity. In other words, that location, we could call it C, that location is going to be discontinuous all the time for infinity. Okay, no matter how far up we go, we can't jump over the wall. I mean, it's always discontinuous. Okay, and those are the different types of discontinuities. We okay with that? Okay, let's go to our second slide. Okay, the first example, they want us to determine whether the following function is continuous at x equals 2. This is point continuity, so we're going to use our great new definition of continuity. All right, so number 1, and when you do your work for me on your daily work and quizzes, tests like that, I would really like for you to number them so that I can follow what you're doing. We are going to mold ourselves into excellent AP BC test takers, because the reader is going to want to be able to follow your work. It can't be scattered all over the world. So number 1, the number 1 thing is that the function value exists. So does h of 2 exist? Let's come over here. Is there a function value at 2? There is, right? It's 4. So number 1, h of 2 exists. That's great. One of the 3 we have complete. Number 2, does the limit as x approaches 2 of h of x exist? Okay, well, let's go work on that. Let's see if it exists. We can do this graphically or algebraically. Why don't we just work on it algebraically? So that would be x plus 2, x minus 2 over x minus 2, and we have a hole there. So the limit coming from, or basically when x is not 2, that results in x plus 2, and I substitute a 2 in there and I get 4. Okay? And then this function value is 4. So coming from the left and the right, or actually technically coming from all around 2 and 2, this is all around 2 and that's 2, we have the same answer. So the limit does equal 4. Check. Our third criteria is that the function value and the limit value must be the same. So the limit as x approaches 2 of h of x must equal h of 2. And in our case, is that correct? Yes. If that wasn't correct, then I would draw a not equal sign here. But that is correct. So therefore, it is continuous. Okay, how is that? That's our first use of this fantastic definition of continuity. Okay, the last 3 are basically we're looking at finding the values of x at which the function is discontinuous and identify the discontinuity type. Now sometimes an example will slide in here where it's really a domain issue more than a particular discontinuity issue. And that really is like this first example. On this first example, this one has a domain issue. And so let's first of all determine where it is continuous. And so let's look at its domain. Now, to do the domains, a lot of times students have trouble with domains. And what I want you to do is I want you to at first consider that every number works. Every number works. And then you start narrowing the field to see what doesn't work. And so in this case, we see there's a radical, and we know that radicals cannot handle negative numbers, right? It turns imaginary. So we know that that's a problem. We're going to have a problem here. Can the radical be 0 in this case? It can, because it's not on the bottom of a fraction, right? It's okay. So I really want 9 minus x squared to be larger than or equal to 0. That's what I want. And hopefully you recall how to solve an quadratic inequality. We need to use sign analysis. And so we factor, we do our sign chart. We see, let's see, if I put a -4 in here, that would be positive. -4, that would be negative. So the section is negative. If I put a 0 in, 0, that would be positive. If we put a 4 in here, let's see, 4, that would be a negative number, that would be positive. So that's our sign chart. We want only positive values. Poor little thing, look, he's so constrained. He can only move between -3 and 3. I mean, that's it. Everything else is wiped out. So, oh well, sorry little guy. So our domain is negative 3 to 3, and I'm including the 3's, right? So because we can be 0. And we could say several different kinds of things. I'm going to say that it's continuous over its domain. It's continuous over its domain. So we identified the domain, and we've said it's continuous over the domain because inside this domain there are no issues. There are no discontinuity issues. So this is kind of an example that's kind of thrown in there with jump discontinuities and holes and infinite discontinuities when it's really actually a domain issue. The domain causes it to not exist somewhere instead of a particular discontinuity. Is that okay? All right, so let's take a look at the next one. So the next one, well, we have a fraction going on, and we know there's always issues, possible issues with a fraction. So I'm going to go ahead and factor. Okay, we discover we have two factors cancel. Do we recall what happens when two factors cancel like that? What happens? We have a hole, right? There's a hole there, and we know now that that's called a removable discontinuity. So at x equals 3, there's a removable discontinuity. Okay. Any other discontinuities? We have a discontinuity at 2, don't we? And that is a infinite discontinuity because that's a vertical asymptote that's there. So this is an infinite discontinuity. Any other problems we need to be aware of? Is there a problem at negative 3? No, it's okay if that's 0, right? That's not a problem. That's okay. So these are our discontinuities. Okay? And our last example, well, there is a lot going on there. We've got arctangent, we've got natural log, we've got algebra. I mean, that is just a lot of stuff. Isn't that exciting? All right, so we need to look at each little thing. Let's think about arctangent. We actually just saw the graph of that yesterday. Does arctangent have any domain issues? Domain or range issues? It has range issues, right? Does it have any domain issues? No, it just went all the way across, didn't it? From negative infinity to infinity. So it doesn't have a domain issue, so we're okay there. It looks really scary, but it's not the culprit here. There is another culprit. Look at that natural log. Oh, that little guy joining that mix has basically wiped out half of the numbers. Darn. So let's think about this natural log. So we know that the argument of natural log can't be negative. Hopefully we remember that, right? The argument or this x value cannot be negative. Can it be 0? No. It can't even be 0. So we've thrown out over half the numbers because it includes 0. So him coming to the party just pretty much wiped half of our numbers out. Okay, that's okay. So let's see, we have other issues down here, right? Let's look at what this is. Now, perhaps let's kind of think through this. We already have been hit pretty hard with natural log, right? Natural log took out 0 and all the negative numbers. What does this add to that problem? Just the 2, right? Because the negative 2 has already been removed by natural log. I mean, it's already out because of this guy right here. So our domain is basically, we can say, lots of ways to say it, 0 to infinity except 2. That's one way to say it, a bit informally. Well, that's one way to say it. So it's basically continuous over its domain except at 2. And what is happening at 2? What's happening at x equals 2? An infinite discontinuity. Infinite discontinuity. Okay? All right, how are we on this? Everybody okay?